Hello everyone, welcome to the webinar. So my name is Chirag. This webinar is being organized by the PyNet Labs, and in this particular webinar we are going to talk about how does BGP works, and we will be exploring all the features about BGP, and we'll be understanding how we can configure BGP in a lab where there is a site 1 which is in a different location, then there is a site 2 which is in a different location. So all such things are going to be discussed later on in this particular webinar. But before that, we need to understand some fundamentals of the BGP so that we can get a better command over BGP. So let's get started quickly without wasting any time, and let's quickly dig deeper into the BGP. So first of all, as we all know that BGP stands for Border Gateway Protocol. And this is basically required for your external communications. Now when we talk about routing protocols, it can be majorly categorized into two categories. We can say that when we talk about routing protocol, it can either be a IGP, Interior Gateway Protocol, or it can be a EGP, Exterior Gateway Protocol. Inside IGP you get two options, the static and the dynamic protocols. Static is simply putting static routes and using the default routing. When it comes to dynamic, we get to see RIP there, we get to see EIGRP there, then we have OSPF as a dynamic routing protocol. You might include ISIS. Then EGP basically includes BGP, that is your Border Gateway Protocol. Now why do we need EGP? That's the question. BGP, or we can say any exterior gateway protocol, is required to make one autonomous system communicate with the other autonomous system. What is this autonomous system now? So we can say that any particular location where a bunch of routers are connected together, it can be considered as autonomous system. So yes, obviously there are some specifications, but to keep things simple, we can understand it in this way. So for example, let's say there are two sites where you have some routers connected. So let's say there is a router 1 connected to router 2, connected to router 3, connected to router 4, like this, and let's say this is your Bangalore site. Similarly, you have a same kind of a setup in let's say Gurgaon as well, where you have some routers connected to each other. Now when we talk about this local communication of router to router, then this can only be configured by IGP protocols like EIGRP, like OSPF, or we can say like RIP. Depending upon your topology and requirements, you can configure any of it. Then similarly here as well, you can put static routes or any dynamic protocol, as I shared, like RIP, EIGRP or OSPF. But in order to make the Bangalore site communicate with the Gurgaon site, you need some external protocol where we get to see BGP, which is Border Gateway Protocol. So Border Gateway Protocol is going to connect your one autonomous system, which is going to contain a couple of routers connected together using some IGP, with another autonomous system, which is again going to have some routers connected together using some IGP protocol like OSPF, EIGRP or RIP, or maybe even static routes. Between these two sites, you will have a connection which can only be built by the protocols like BGP, which are basically external gateway protocols. Now when I say that I connect my autonomous system 1 with the autonomous system 2, then do we have any identification for them? Yes, we do. So just like you get a public IP, you can also register for autonomous system numbers which are provided by the organization INA. We will have a look into the working of INA, how there are different registries for different locations, how things are working there. We'll get to that. But as of now, we can say a number is provided by this INA organization which will be very unique to your organization. So if I say that I have autonomous system number 10 here on the Bangalore site, then this 10 cannot be there anywhere else in the world. This is going to be very unique to me. Similarly, you will have some autonomous system number for the Gurgaon site, let's say 20. So in order to connect this autonomous system number 10 with the 20, you need BGP, or being specific, you need Ebgp. So BGP also contains two types of neighborships, Ibgp and Ebgp. Again, we will talk about that later on. That is not our topic as of now. We'll get to that. So between this autonomous system number 10 and 20, we need a BGP connection so that they can communicate. Now, what else could be the situations where you might need BGP connectivity? Do we require BGP when we are getting connected with our internet? So let's check that also. When I say I have a LAN connectivity, let's say this is my router of my organization and I have a layer 3 switch connected to my router. Then after that layer 3 switch, I have some access layer switches, and then some end devices are connected, for example, like this. Then this router is getting connected with ISP. This is my ISP router. So in this organization where I have this edge router, let's say R1, I have just one internet connection and all my data transmission depends upon that. So do we need BGP there? No, we can simply use a default route. We can simply put a default route on this gateway for this ISP router, so that my all data which is willing to communicate with internet or maybe any other particular network which is connected to me over a different site can directly go to the ISP device, and then ISP can route it further depending upon the destination. So we don't need BGP here. We can simply achieve this by static routes. Then let's say now my router 1 is connected with another ISP. This is the ISP 1 and this is my ISP 2. So I have kept another ISP connection so that in case my ISP 1 goes down, then I don't have to get disconnected with the other sites or other locations. I can still stay connected using my ISP 2. So in such situation, do we need BGP? Again, no. We can simply configure static routes here as well by defining the metric. We can manipulate the metric to define one of the route as the primary one and the other one maybe as the backup route, which will get into routing table once the primary one goes down. Or you can also perform load balancing here for dividing the data over your ISP 1 and ISP 2. So where do we actually need BGP? That's the question now. So the first thing is, when you have multiple ISP routers, when you have multiple ISP connections connected to your multiple edge routers, then in those scenarios you will need BGP. For example, if I say I have another router and that router is also connected to ISP 1 and ISP 2. So in this scenario we might need BGP. Or if there is any server which you want to be hosted over the internet, then that case is something where we require BGP only. For example, again, let's say you are working in some organization and you have this router at your data center. Then there is a switch connected to the router, and then we can say there is a server. Now this particular router is connected with ISP and my other sites are also connected with ISP. Let's say I have a location in Dubai, let's say, and we have a switch there and we can say around thousands of employees sitting there. Then we also have another site in, let's say, London, and there also you have employees sitting in. Now this server is hosting the application which is required by these 1000 users or by these 600 users, which are my employees. So if you know, in some organizations there are some specific applications which are used by the employees, and the employees can only be able to access these applications which are hosted over some server which is not even connected to me directly, or I would say is not nearby to my location, then also they can communicate, because this server is hosted over the internet and they are also getting connected with internet, so they can simply make this communication possible. So in this scenario also, when you are willing to host your specific server over the internet, in this type of a scenario, you will need BGP only. You cannot work with RIP or OSPF to do such type of a thing. So we can say that when I want these Dubai and London branch employees to have the access of this server, or to have the access of the application which is being hosted by this server, then I need BGP. I need BGP here so that I can basically advertise my server over the internet and my employees can take the access of that. So these are few scenarios where you might observe BGP working and you might have to configure it to make things work. Now, as I said earlier, INA is the organization which is providing us the public IP, and along with that the autonomous system numbers are also provided by the INA. Now, when you are basically an organization and you are willing to appear in the public, or when you are willing to get a presence in the public network, then you need an autonomous system number, and that autonomous system number is going to be very unique for you. So what is the range of these numbers? That's another question. So INA can provide you autonomous system numbers from the range of 1 to 64,511. These are going to be globally, we can say globally unique autonomous system numbers. Then there is a private range as well, which can be used for testing or other purposes, which begins from 64512 and ends at 65535. So 65,535. These are basically the private ASNs. Then this is basically your 2-byte range. So 2 byte means 16 bits, and if you do the calculation, so 2 raised to the power 16 gives you 65536. So that is what we are using here as well. Now there is another range of 4 bytes where we have around 0 to 4.2 billions of autonomous system numbers in the range, and out of which the last 94 millions are private ASNs. Out of these ranges, basically you are going to get some autonomous system number, and then using the configurations of BGP, you can make your autonomous system number communicate with the other autonomous system number. When we talk about making one AS communicate with the other, there we need eBGP. So my BGP neighborships are of 2 types. It can be IBGP and it can be eBGP. IBGP would be in same autonomous system, and eBGP will be there in different autonomous system. If 2 routers are there in the same autonomous system, then, and if I am configuring BGP between them, then I would say that it is going to be a IBGP network. Similarly, let's say there is another site where you have 2 routers connected together, then we will simply say that if there is BGP communication between them, then that is also going to be IBGP. Let's say this is my autonomous system 10 and this is my autonomous system number 11. Now when I will connect this particular router from AS10 to this particular router, which is from AS11, then this is going to be a eBGP neighborship. So when the neighborship is happening between 2 different autonomous system numbers, then that means it is going to be eBGP, and when it is happening within the same autonomous system number, then that simply means it is going to be IBGP. Now BGP is totally for external communications. Then what, this is the question in my mind, that why do we need IBGP then? Why can't we just simply use OSPF or EIGRP to make the routers communicate internally? So in scenarios where you need to exchange those public routes with the other router, you need Ibgp only. It cannot really work ahead with the OSPF or EIGRP communications. So for example, let's say you have a branch where you have, let's say, 3 routers. Now I have an internet connection connected to my last router. This is going to be my ISP1. Then I also have an internet connection here. Now in order to bring redundancy here, to make sure that this particular ISP2 connection can get into picture if, let's say, my first one goes down, we need to create Ibgp network so that the public routes which are going to be received over this router can be shared directly with R3, and the public routes which are going to be received over the ISP1 network can be directly shared with R1. And obviously between R1, R2 and R3 you can use any of the IGP protocol. So we don't need Ibgp, we don't need Ibgp between R1 and R2. There we can use EIGRP OSPF. But yes, we do need between R1 and R3. There we need Ibgp. And we can say that between R1 and the router of ISP there is going to be Ibgp, because that's going to be different autonomous system numbers, right? Similarly, here also we will have Ibgp. Now we have talked about a couple of things. We have discussed that how Ibgp and Ebgp are different. Then we have also learned how autonomous system numbers are assigned by the organization called INA. Then we can say that we have discussed how basically a BGP can make one autonomous system number communicate with the other. Now the thing is that what are going to be the autonomous, the administrative distance of the routes which are going to be learned via BGP? That's the question. So when I say that my routes are learned via Ibgp network, then that's going to be there with a AD value of 200, and if it is from Ebgp, then it is going to be 20. So the AD of Ibgp routes is going to be 200 and AD of Ebgp route is going to be 20. So from this only we can judge that BGP is more of an external protocol. It is not created for your internal communications. For that you have some other protocols like OSPF and EIGRP. Then that's how it works. We will try out some of the labs. We'll see how Ibgp network can be created or how Ebgp neighborships can be created. Now while doing the labs we will discuss some more pointers about how BGP works. So let's get started. I'll quickly share my other screen where I have the lab setup ready for you guys. So here it is. Now in my first scenario, R1 and R2, these are basically connected over BGP 100. Now I know this is not a private BGP, but since this is just a virtual environment, we can use any of the number there. But in case you are dealing with the production scenarios where you need to test out something, then you will be obviously using some private autonomous system numbers. So I have both the routers in the same BGP. So that simply means that these two routers are going to maintain Ibgp network because they are a part of same autonomous system number. Then similarly, if a router is in BGP 11 and the other router is in BGP 22, then they are going to create Ebgp connection or Ebgp neighborships. So let's get started. Let's try to configure Ibgp neighborship first between R1 and R2, and let's understand what is the commands which would be required to do this configuration. So I'll open the CLI of router number 1 here, and just a second, there. So this is my router number 1. I'll begin my configurations here. I'll say enable config t hostname R1. I haven't done any configuration on this router as of now. So we will first of all put the IP configs. So interface gig 0/0 IP address 12.10.1.1 255.255.255.252 because it's a /30 network. No shutdown, exit. That's it. Then I'll move to router 2. We'll put the IP address there also. This is the CLI of router number 2. I'm going to say enable config T, hostname R2, interface gig 0/0, IP address 12.10.1.2, 255.255.255.252, and then I can simply say no shutdown to make the port up, exit. After this, the task is to make IBGP connection between my router number 1 and my router number 2. That's the main thing which I am going to configure here. Now, for that, we need to make sure that over the interfaces where you want connectivity, the interfaces should be able to communicate with each other. So if I am on router number 1 and if I say I want to ping 12.10.1.2, then I should be getting the reply. Then only I can create a neighborship over that particular IP address. So we can make sure that we are able to reach that by saying 12.10.1.2 like this. And we are getting the replies, right? So let's begin. Now let's put the configurations. I'm going to say config T and then router BGP 100. After this, we need to define our neighbor. It is not like the dynamic protocols we see in our IGP networks. It is basically where you define your neighbors manually. So you will say neighbor and put the IP address of the neighbor. What is that? It is 12.10.1.2. What is the autonomous system number of your neighbor? That is something which you define as remote autonomous system, remote-AS. So it is also 100. Now using this information that in what particular autonomous system is my neighbor participating, it decides whether it is going to be a IBGP communication or neighborship or whether it is going to be a eBGP neighborship. When I hit enter, I can say exit. Then I'll go to the router number 2 and we'll put the BGP configurations there as well. Router BGP 100, then define my neighbor as 12.10.1.1, 255.255, okay, 12.10.1.1 remote AS 100, and then we can say exit. Then after we can say after some seconds only, it gives you this log which says that neighborship with 12.10.1.1 is up. That's how you build IBGP communication. Now this was a very simple scenario. In this topology, which I have also created for you guys to explain you things better, in this topology we have a site number 1 and we have a site number 2. This is going to be a different autonomous system, this is going to be a different autonomous system, and this is my ISP cloud. I want you guys to try to question yourself that where will be IBGP required? When the routers are in different AS, at that time I need eBGP networks, right? I need eBGP neighborship. So it is not something which will be used between edge 1 and your ISP 1. So that's clear. Now between BGP 10 and BGP 20, they are again different AS. That means I'll not be using IBGP between ISP 2 and edge 2 obviously. So between ISP 1 and ISP 2, they are both a part of same autonomous system. This is the scenario where you will need IBGP so that your external routes can be communicated with the other router. Similarly, as we know that we cannot really work with just IBGP or just with eBGP, we need to also deal with eBGP neighbors. So let's understand how eBGP neighborship can be built, and after that we will try to configure this topology where I have a site connected to internet, then another site connected to internet, and we'll try to make these end devices communicate with the server. So first of all, our target is to learn how eBGP neighborships are built. So I'll go back to my another topology where I have 2 routers and I need to put eBGP communication between them. So first of all, I'm going to go to router number 3 and we'll put the basic IP configs. This is my router number 3 and there we go. So we'll say enable config T, hostname R3, interface gig 00, IP address 34.10.1.1, use the subnet mask, say no shutdown and exit. Then we will jump on to the router number 4 and we will configure the IP address there as well. Enable config t hostname R4, interface gig 0/0, IP address 34.10.1.2.255.255.255.252 and then sudo shutdown exit. Now it's time to configure eBgp networks between them. So we will go to again router 3 and we'll create a BGP process which is going to be BGP 11. Now there is another important thing to understand, that BGP process can only be created, only one BGP process can be created on any particular router. You cannot have more than one BGP process on the same router. So I'm going to say router BGP 11 and we'll define my neighbor as 34.10.1.2. Now the question is, what is going to be the remote autonomous system? Now since my neighbor is participating in BGP 22, I will say that my remote AS is 22, enter. Then I can simply take the exit. Right now we are not looking at how we are supposed to advertise the network. We will observe that in the previous topology which we have discussed. Now we have configured router BGP 11, inside which I have defined the neighbor, and the remote autonomous system is going to be 22. Now I'll go to router 4 and on router 4 we will try to configure BGP so that we can have a eBGP network between R3 and R4. So we will simply say router BGP 22 this time, and my neighbor is going to be 34.10.1.1 and my remote AS will be 11. Exit. Let's wait for the log to come up which defines that the neighborship is built between R3 and R4. There you go. It tells you that the BGP neighborship you were trying to create has been successfully established, and now you can advertise your routes from BGP 11 to BGP 22 and similarly from BGP 22 to BGP 11. That's how your eBGP works. So as of now you must have got some basic idea that how BGP configurations look like. You simply create a process, you define the network, you define the neighbor, you define the autonomous system of that neighbor, and that's all. It's done. The rest things are basically advertising the networks. Then there are few of the complications which get into picture, where we have a lots of routers in our topology, where you might have to increase the multi-hop count, where you might have to update the sources as your loopback interfaces and some more things. So all such things we are going to focus on that also. That's an also important part of BGP, but for that we have to get prepared ourselves with the fundamentals of BGP. So we are somewhat good with the configurations of how IBGP neighborships or how eBGP neighborships can be built. Now it's time to get on our real topology, which we are looking forward to understand BGP networks. So it's time to configure this. This is my site number 1. Let's first of all understand what's going to happen here. So this is my site number 1 on the left side. I have an edge router, then I have a LAN connected to it. Then this edge router is getting connected to my internet through ISP. Then I can say there is another ISP router connected with ISP1, which are both participating into BGP 10. Then on the site number 2, I have a router which is connected with ISP, and we have a BGP process here, BGP 20 running in these sites. And also there is this application server which we want to host over the internet, so that my employees sitting here in this site can take the access of that particular server and can basically use the application. So that's going to be the scenario. Now as per the discussions we have done, we really don't need BGP communication here, right? We don't need that. We can simply put a default route towards my ISP and my devices will be able to communicate with the internet. I don't really need to put a BGP communication or create a BGP neighborship between them. But is it possible to make private network communicate with internet? No, obviously no. So for that we have network address translations. So we are going to create a NAT rule on router number, we can say edge 1, on router edge 1 for this private network 192.168.1.0, and we will ask this router to translate these IP addresses onto the public IP 12.10.1.1 or to whatever it will be configured. Then this particular LAN will be able to communicate with the internet, as we will have a default route on my router for the internet, or we can say for the ISP. And on the other side, since I want to advertise, or we can say since I want to host my application on this application server, I would need a BGP communication between my internet router and my edge router. So we are going to configure BGP on this side, and simply on the other side we can use the default route. So let's quickly get started and let's begin the configuration from edge router 1. I'll take the CLI access here. This is my edge 1. Let's begin the configurations on this. I'm going to say enable config t. Then we can say host name is going to be edge 1 only, let's say. Then on interface gig 0/0, I will configure the IP address 192.168.1.1. 255.255.255.0 will be my subnet mask, and then I can run the no shutdown command to make it up. Take the exit. Then we'll go to interface gig 01 to put the IP on that as well. So interface gig 0/1, IP address 12.10.1.1, 255.255.255.252, and then say no shutdown. Exit. Now for my LAN network, I will also configure DHCP. So I'm going to say IP DHCP pool A for the network 192.168.1.0, 255.255.255.0, and my gateway address is going to be 192.168.1.1. Exit. Now let's jump on to ISP1 and put the basic configurations there as well. This is the CLI of my ISP1. I'm going to say enable config t host name ISP1. On interface gig 0/0, I will configure the IP address as 12.10.1.2, 255.255.255.252, and then I can say no shutdown. Then on interface gig 0/1, we are going to configure the IP address 23.10.1.1, 255.255.255.252, and then no shutdown. Exit. Like this. Then I'll go to ISP2 router, put the basic IP configs there also. Enable config t host name ISP2, interface gig 0/0, IP address 23.10.1.2, 255.255.255.252, and then say no shutdown. Exit. On interface gig 0/1, we will configure the IP address as 34.10.1.1, 255.255.255.252, and then no shutdown. Exit. Now it's time to configure my edge router 2, which is going to be there on my site number 2. So I'll go to that. This is my edge router 2. Say enable config t host name edge 2. On interface gig 0/0, I'm going to configure the IP address as 34.10.1.2, 255.255.255.252, and then say no shutdown. On interface gig 0/1, we'll configure the IP address as 45.10.1.1, 255.255.255.0, and then say no shutdown. So if I show you the IP addresses here, do show IP interface brief. then it is 34.10.1.2 on my gig 00, which is connected over the which is connected to the ISP. Then on gig 01 it is 45.10.11 with a /24 subnet. Now my next task would be making the connectivity. So I'll go to edge 1 and will simply put a default route for the next hop as ISP1. Then we will also configure the PAT configuration on edge 1 so that my private network can be translated to the public network and it can communicate with the internet obviously. On this router, I'm going to first of all create a default route by saying IP route 0.0.0.0 space 0000, and the next hop will be 12.10.1.2, which is my ISP router. After this, let's create a ACL for defining our private network. So we will say access list 10, just a standard access list, and we are going to permit the network 192.168.1.0 with the wildcard mask 0000255. After this, we are going to create a NAT rule so that my private network 1.0.192.168.1.0 can be translated to the public IP 12.10.1.1 provided by my ISP. So I will say IP NAT inside. So IP NAT inside basically refers to the private network. IP NAT inside source is going to be the network which is defined in list number 10. And what do we want? We want the translation. On what particular interface? We want the translation to be happening on gig 01, which is the one which is connected to the public networks, right? So I'm going to say I want this private network which is there in the source list 10 to be translated on interface gig 0/1 through the PAT method. For that we will use the keyword overload like this. Then let's apply the NAT rule. As I said, inside is going to be the private network and outside is going to be the public network. I'll apply it on gig 00 by saying IP NAT inside, because that's the interface which is facing my private network. Then I'll go to interface gig 0/1, interface gig 0/1, and on this particular interface I'm going to say IP NAT outside. There are some logs coming up because of incomplete configuration, so IP NAT outside there. After this, we can expect that my private network will be translated to the public network. Now I have basically configured my edge router 1 completely with the NAT configurations as well as with the default route. Now when my network or when my packet reaches ISP, then there should be some BGP, or we can say there should be some communication between ISP1 and ISP2 as well, so that this public network can be advertised to the ISP2 and ISP2 can learn about the data coming from this edge router. So for that we will use Ibgp neighborship between ISP1 and ISP2. So I'll go to ISP1, and as we have already learned that how Ibgp should be configured, we will put the configurations for that. So on this ISP1, I'm going to say router BGP 10. My neighbor is going to be 23.10.1.2 and the autonomous system of my neighbor will be also 10. Then I will advertise the network using this command network, then define the network ID 12.10.1.0. this is my network ID. Then define the mask by using the keyword mask 255.255.255.252 like this. Exit. We have advertised this network so that my other routers of ISP cloud can learn about this, and in case they get some packet, they can route it according to this. Now I'll go to ISP2 and will put the configurations there. So this is my ISP2. I'm going to say router BGP 10 here. Then I will define my neighbor as 23.10.1.1 and my remote AS is also going to be 10 like this. After that, we will also advertise the network 34.10.1.0. So I'm going to say network 34.10.1.0 and mask 255.255.252 like this, and we will take the exit. Now if I check my routing table here on ISP2 by saying show IP route, then there is not any route installed, though we have already advertised it from ISP1. Like we advertised 12.10.1.0 from ISP1, and we have also advertised 34.10.1.0 from the ISP2, but they are not installed on these routers. We will look into the reason behind that later on. As of now, we just have to keep in mind that there is something which is yet to be configured so that they can basically exchange the routes with each other. Now we will move to the third part, which is configuring BGP 20, and we will create a eBGP communication between your ISP2 and Edge 2, and we will advertise this particular host, or we can say this particular server, so that these employees can communicate with this server. So I'll go to that Edge 2 router. There it is. On this Edge 2, we will create the BGP process 20 by saying router BGP 20, and this time my neighbor is going to be 34.10.1.1. The autonomous system of my neighbor is 10, and I want to advertise the network 45.10.1.0, because in this network there is a server which I want to be hosted on the internet, so that my employees which are sitting in the other location can take the access of this server. So I will advertise this network using the mask 255.255.255.0 like this, and we will say exit there. Okay, now let's check the routing table of R1 again. Okay, we still have to configure BGP from ISP2 to build the neighborship, so let's complete that first. I'll say config T router BGP 10, neighbor is going to be 34.10.1.2, the remote AS is going to be 20, and we can take the exit after this. Show IP route. So the time it takes basically to exchange the route is done, and we can see that 12.10.1.0 is added, but you will not observe 45.10.1.0 into the routing table. But if I say show IP BGP, then we can see that 45.10.1.0 is there in my table, but this will not get installed into the routing table even if we wait for 5 minutes. The reason behind that is, okay, this is ISP2. On ISP2 it will get installed, but on ISP1 it will not get installed because of next hop configurations. So on router 2, the next hop is 34.10.1.2, which is pretty correct, right? So ISP2 should be reaching 45.10.1.0 by giving the packets to 34.10.1.2. But let's check the detail on ISP1 also. And when I say show IP BGP there, I can see that 45.10.1.0 is there in my table, but the next hop is 34.10.1.2. So from ISP1 we cannot really communicate directly with 34.10.1.2, right? This is something which you have to fix by running a specific command so that the next hop can be updated to the correct one. For ISP1, in order to reach 45.10.1.0 network, in order to reach from ISP1 this particular network, we have to give the packets first to ISP2, right? But when ISP2 gave the network 45.10.1.0, it gave it to ISP with the same next hop, which was 34.10.1.2, as we can see. That is the reason this particular route will not be installed in the routing table of R1, or we can say ISP1, which we can see in our routing table. It is not there, right? And how do we make this update? We make this update by going on to the neighbor and defining that for ISP1, my routes which I am going to send should contain the next hop as myself. So from ISP2, we will run a command we'll go into the BGP, router BGP 10, and then we will call our neighbor here 23.10.1.2. So we are telling the BGP process that for my neighbor 23.10.1.1, I want to give the routes with the next hop as myself. So next hop self is the command which you have to execute. Neighbor 23.10.1.1 should be given the routes with the next hop as myself. And when you make this update, you can look into the table again on R1. This is my ISP1. I can see that show IP BGP table. I can see that the next hop is updated successfully to 23.10.1.2, which is router number 2, or we can say ISP2. Earlier, when we looked into this table, 45.10.1.0 network was there, but it was there with the next hop as 34.10.1.2. But after updating the next hop from router 2, we can observe that next hop is corrected. And if I look into my routing table, then the route should also be added. There you go. 45.10.1.0 network is added. Now let's try to make them communicate. Let's put the IP addresses on the end devices also. I'll go to these servers and the VPC to put the configuration. So for VPC 3 and 4, we have already configured DHCP. I'm going to say DHCP there. And on VPC 4 as well, we will say DHCP. Okay, we got the IP 192.168.1.2 and the gateway is 1.1. That's correct. Now we will go to this server. The server which I have taken here for the explanation purpose is also a VPC only. So the image is of VPC itself. So I'm going to put a static IP on this so that we can see if the communication is happening or not. We will say IP 45.10.1.2/24 and the gateway will be 45.10.1.1. We got the IP, we got the subnet, we got the gateway. Now it's time to check the communication. So I'll go to VPC 3 and we'll try to ping this application server. So when I say ping 45.10.1.2, then we are getting the reply. So that simply means that our all configurations or all the BGP advertisements are working correctly. And the thing which is happening here is, now packet will be traveling from VPC to the edge router first. On the edge router, it will be translated from the private IP to the public IP, which happens because of the NAT communications NAT configurations. Then from this router, it will go to ISP1 using the default route. From ISP1 to ISP2, it will be going ahead with the Ibgp connectivity. From ISP2 to Edge 2, it will go using the Ebgp connectivity which is there. Then from this particular router to this, we can say that they are both directly connected, hence it will forward the packet to the dedicated server and the communication happens like that. So that's how your BGP can be utilized in order to advertise your servers from one particular site. And in case you just have a single network connection of your ISP, then you don't really need BGP there. You can make it work through default route as we have already observed here in this topology. So if you guys have any questions related to the concept or related to the any configurational part, then you can let me know in the chat box. Alright then, I think we are good with this, and since we don't have any questions, we are good to wrap up. I hope you guys enjoyed the session and you found it informative. This is not done. I mean, what I mean to say here is that this is not the whole BGP. BGP is a vast protocol, and we can say that this basically is just a part of the configuration. It includes a lot many things which can be observed in different topologies, in some topologies containing more routers and more devices, or maybe more networks. So there can be multiple scenarios where you might put manipulators, where you might use PBR to do various things. So all such can be achieved with BGP. This was just an explanation to help you understand how actually your internet works, or how actually one site can communicate to the other site using internet. So I hope I was able to explain that successfully. Thank you so much, guys. I really enjoyed this session, and I hope the same goes to you as well. So I'll see you in some other training or in some other session again. Thank you so much.